Welcome back, everybody, to our second afternoon session, in which we are going to give you some insight of the Ocean project. So we have changed the agenda a little bit since today in the morning, due to some technical difficulties. Professor Gabriel Senti could not give his presentation as a general overview of the Ocean project. He's going to give it in this session. So he will be giving two presentations after each other, followed by another colleague of his also on the Ocean project. So Professor Gabriel Senti is professor of industrial chemistry at the University of Messina, president of the European Research Institute of Catalysis and the International Association of Catalysis Societies. He is a recipient of the Humboldt Research Award, ERC Synergy Grant, and PIFI Award for the Chinese Academy of Science. And Professor Senti is going to give a presentation now about the general overview of the Ocean project, followed by the presentation of electrode synthesis and properties. Professor Senti, the floor is yours.
Many thanks for the introduction, and let me just apologize all the audience for the technical problem that we had this morning, but you know that Murphy law is the only which always work in all ways. So let me now to move. I hope that you will see the slide because I don't have a view of them, and the Ocean project, I think that we have seen is part of this, let me say, cluster of projects which arrive to demonstrate the effective possibility to use carbon dioxide from real emission, and this is demonstrated also on a pilot scale. I think that the one difference in terms of Ocean, and which is part also of his ambition, is that we don't like only to demonstrate it is possible to reuse carbon dioxide, and that electrocatalytic routes is very valuable to go in this direction. But also we try to establish a new value chain, especially to produce C2 product from carbon dioxide, which is this a kind of peculiar aspect of the project. So let me now move, and I will to next slide, the number 2. I hope that you see. Well, this is the general view of the project. What are the participants? You see that we have various companies, Avantium, Edway, and Gascatel, Isitec, and other, plus a series of university and research institutions. Altogether, I think that have formed a very good project which work in strong synergy. And the project is officially already ended, but we had an extension up to July this year because we was affected also by this general pandemic situation. The project is coordinated by European Research Institute of Catalysis, which I'm presiding, which is an association different research institute over Europe. So let me now move to number 6. I will skip some of the slides just to make a bit shorter. And I think that these are the general objective of that we have in terms of electrification of chemical industry. There is a renewable interest, and we have seen that there are many projects starting on this, but up to now, there are still limited electrochemical process in chemical area, apart some which are very like the chlorous soda process. But in this case, I think that the main challenge that we have is that we have the problem of selectivity, and to create also new value chain for this. And this is the main difference that we have in the project. But of course, if we can move to the next slide, at the number 7, electrocatalysis is offering also a number of possibility to drive chemical reaction. We are using, I think that was already remarked that this morning, less expensive starting material. Of course, carbon dioxide is formally a waste and we can reuse. We have less aggressive process condition. We are operating close to room temperature and ambient pressure. We can also replace some polluting chemical reaction with more environment friendly. We especially important, we have process intensification. We are reducing the process steps, and this will be both very important. Especially we can integrate both cathodic and anodic reaction, and so we can make two reactions at the same time. And of course, we have also other advantages. Next slide, number 8. What is the peculiar aspect I have already mentioned for the Niederaussem project is that we are creating a new value chain from carbon dioxide going to C2 product that you see on the right part. We first synthesize formate, then we have a transformation of formate to oxalic acid. This can be either thermal or electrocatalytic. And then we are reducing either thermal, but especially electrocatalytic, oxalic acid with product like glycolic acid or glyoxylic acid, and eventually, finally, also to ethylene glycol, which is a very large product. And you see that when you convert from this side, you go to a different kind of market, but especially you can go also to very high added values. Glyoxylic and especially glycolic acid are very valuable monomer for new kind of polymer, high performance polymer. Ethylene glycol is already a well-established market, and so we create really an added values in going to this direction. Next slide, number 9. What is the concept? We started from a technology that was acquired by Avantium from US, acquired from Liquid Light, that was using formate. This was on a scale, a laboratory scale demonstration. Then this was upgraded up to TRL 6 in the project. And then this technology, electrocatalytic to synthesize formate from CO2, is integrated with other important elements. One is the paired reaction, which is the glucose oxidation to form glucoric acid. The other is the integration with downstream, so transformation of formate to oxalate. And then, of course, you have a salt, and we can also use electrochemical technology for converting the salt to the acid, both which is valid for oxalic acid and formic acid. And then we can use and upgrade these. For example, you can have hydrogenation or electrocatalytic hydrogenation to form a glycolic acid, for example. And then we have also addressed the use and the formation of polymer from this product. So the full chain is addressed in the project. Next slide, number 10. So we have organized the project in 3 steps around. The first is, well, developing the basic methodology to upgrade up to TRL, something like 4. Then, of course, optimization, engineering, and manufacturing of the demo unit to arrive to TRL 5 and study the different compound. And finally, the last part is related to testing and demonstration on industrial scale TRL 6. We don't arrive to all element of the process. This is just only for the demonstration of the electrocatalytic part. Some other element, for example, the bipolar membrane or the formation of other product, are a bit lower TRL level. And of course, combined with these are the classical, let me say, action like life cycle analysis, which is of course very important, business case, exploitation strategy, dissemination, and then training, and of course, coordination of the project. Next slide, number 11. What is the role of the partner? We have a series of industrial partners, at least 4, and fortunately one of these was going to bankrupt, and so we was forced to eliminate this partner. And then we have 2 research institutions like European Research Institute of Catalysis and the Italian Foundation of Technology. Then finally the RVA, that is the industrial demonstration, and also University of Amsterdam, which is dealing on polymerization and hydroformylation. Next one. This was the starting point for the project. Essentially, we were started from already lab scale, but a bit higher even starting point, demo shell to synthesize the formate, and you see the small scale. This was up 100 square centimeter, but the initial one was even lower, something like 10 square centimeter. This was already this picture of a kind of after 1 year and a half of the research activity. Next one. Then, of course, it was the activity ready to scale up and stack the electrocatalytic reactor. You see that we was arriving to an electrochemical cell, which is formed something like 200 square centimeter each plate, and was 2 stacks put it together. You see here the dimension of the cell and well, the general scheme of how they are assembled. Of course, is already a size which is important, and in which you start to see all the problems which are arising typically when you have this industrial size electrocatalytic reactor, in which you need to have a very good distribution of all the elements to avoid any bypass and similar kind of problem. So it was not easy to prepare the sample and to arrive to obtain good performance with this size. And then finally, the demonstrator, you have seen already some element, and there is a movie at the end of this presentation to show that the unit is in a container. You see some of the element on the right top. You see the electrode, which is inserted in the system, and then some of the other elements, which are the electrolyte container to circulate and so on. So the next one, number 15, you see inside view of the Awesome demonstrator, which is fully automatized, that can work 24 hours per day. You see that there is a part in blue, which is the cathodic side, a part in green, which is the anodic side. In orange is the cell that we have seen before, and then of course you have all the elements for controlling and so on, electric component and so on. You see that at the end is a really small size to arrive to already good production that you can have. Next slide, 16. What is important is that we have inserted also an integrated monitoring of the performance, because of course, when you go to already to size which is significant, then you can have easy possible deactivation or broken some element and other. So we have integrated electrode monitoring by impedance spectroscopy, and you see here some of the elements that you can see immediately if something happen, if there is a loss of performance and so on. Next one, the number 17. Here is the part to convert formate to oxalate. Also, this is in a size which is compatible with TRL5, and this is a thermal part. Was also this. We have a number of initial difficulty to develop this system, but now is optimized. But was not simple, even if his thermal reaction is not simple to control all the performance. The 18. Then we have also, of course, developed some electrocatalysts. I will speak in few minutes a bit more on this, so I will skip for now. 19. Finally, of course, very important part is all the analysis by life cycle assessment to be sure that what we perform is really a reduction in the carbon dioxide and not something which is masked. So it's not enough to say that we are reusing carbon dioxide, but we need to demonstrate that we are decreasing up to the level that we was promising. So this is one element. For example, you see the different flow or what is the impact in terms of carbon dioxide equivalent to form glycolic acid starting from all the elements. Of course, we have performed the full life cycle analysis of all the other part of the system. So next slide. This is the final summary before to have a short video. We arrived to a prototype which is running, and up to now everything is going quite well and is working very well. It was proof, and especially we are creating a new value chain for from carbon dioxide, and we hope that this can arrive also to implementation on large scale. So I hope that will be possible to start now. The video is 2.5 minutes video, so I will not comment that there are some indication, so I think that will be more simple that I will start the next presentation at the end of this meeting. So let's try to start the video. So what you see here is the pilot unit which is arrived, and they are mounting, and you see here the first validation test that was made at Avantium. Then here is arrived hardware, and they are mounting. So now is open. And you see the inner part that is what I have already described. This is the cell. These are some of the connection line and so on. And of course, these are two stacked cells, but you can increase the productivity by putting more of these together. So you see here some of the other elements that are well, necessary, the reservoir for the electrolyte, for moving, and so on, and some of the other components. And this is all the view of the system. So you see that by just only this relatively small reactor, you form up to 30 tons per year of formate solution. So which is ready, so you can imagine that it is very easy to scale up of this system, because essentially largely is to have more stack and also more units. So essentially the scale up is by numbering, and of course this gives you flexibility in operation. So you see it is fully automatized, and the people was trained to manage, but at the end is a really simple solution. So, and here you see that if you like to have more information, here are some of the social links where you can have more information on the project. So let's now move a bit more on some, let me say, technical aspect of the electrode. So I hope that you will start the second my presentation. So if so, please move to the second slide. Which is the path diagram of the activity that you have seen already before, but in which in yellow are highlighted some of the part where electrochemistry play a role. You see that is not only in the demo unit that we have seen that was arrived to pilot unit, but also play inside the project, also in the pilot electrosynthesis, in the technology for acidification of carboxylate, which is also an electrochemical system, and also in terms of the hydrogenation of oxalic acid, especially particularly to the initial target was ethylene glycol, but then we have seen that it will be better to arrive to glycolic acid, because it is an added values and interesting product also for polymerization. We have tested this also in terms of comparison between hydrogenation, classical thermal, and electrocatalytic hydrogenation. And I can say that at the end, we have shown that if you have a good electrocatalyst, we will see that we have developed some original type of electrocatalyst. Then to make by electrocatalytic is advantage with respect to the gas phase, because essentially what you avoid is all the cost which is related to putting gas phase the reactant. You have an aqueous solution, which is, let me say, relatively diluted. Then, of course, you spend a lot of energy to have gasification of this. And so this is the reason why electrocatalytic hydrogenation has a clear advantage of this. Besides the general aspect that you avoid to use hydrogen because you produce on site from water. And for this reason, you avoid to have all the side impact related to producing hydrogen. So next slide number 3. So let me start to give a brief overview of the different activities that we have in this different section, where we had the role of electrocatalysis and so on in this way on preparation of the electrode. The first one is related to work package 1, which is carbon dioxide reduction in the demo cell. That is at the end is arrived to a pilot unit, and here you see that mainly are company Avantium, Gascatel, Isitec, and Edway, which are involved in this activity plus some, let me say, assistance by Eric. And here the main problem respect to the starting point was to increase the stability. And this was, we have realized that very important to increase the stability is not only the catalyst itself, but the condition of operation, which are very, very important. And also optimize the performance, so to optimize the design and the preparation of the gas diffusion layer and gas diffusion electrode itself. And of course, then assemble all together to develop the demo cell and to scale up the system. Now, as mentioned, the system in pilot scale is running in terms of testing up to TRL 7. Next slide, the number 4. Here you see, for example, initially we have a stability that was of the order of 2 hours, 2-3 hours. And then we improved the performance, especially in terms of design of the cell, and was possible to obtain stability over 100 hours and even more. I apologize that due to confidentiality issues, I have avoided to put the number in terms of the performance, but let me say that these are relatively high performance, which are quite good also for industrialization of the system. Next slide, number 5, we see that, of course, what's necessary to develop and scale up the preparation. Let me say, preparing also the catalyst, and here, of course, it was the typical problem when you scale up the preparation. You need to make this not only on larger scale, but also in conditions which are relevant from industrial perspective, so minimization of waste, to obtain high homogeneity, to obtain a high level of metal recovery, and so on, because of course this is important. And then to transform this to a GDL electrode, you see the rolling system. The electrode that is prepared is a gas diffusion electrode, and can be we use a size up to 200 square centimeter, but you see that the preparation can be already made in order that this system can be very easy scale up to larger size, but also to higher number of stacks. What is important is that what you need is to obtain very homogeneous performance and very high Faraday efficiency at high current density, and we achieve to be even more than the limit that we put of 100 milliampere per square centimeter. Next slide. You see here some other element that we have already seen before, or some of the design of the different trial and that we made up to arrive to final preparation of the cell. As I say again, is a two-stacked cell with a total electrode area of something like a half square meter. Next slide. Of course, this is now under validation, and we have seen that even after operation, there is a good performance, and we see that up to when is arrived to, well, conditioning, after the conditioning phase, then there is a stable performance, density, current, and potential, which is reached by the cell. Next slide, number 8. The other element is to develop the paired electrosynthesis. This is the work package number 2, and also here mainly are a company which are involved, plus Eric and IT. And here the objective was to scale up the paired electrosynthesis. At the end, we we was trying before different reaction, but at the end, we arrived at the best combination is to use the glycerol, which is that is a side byproduct of biorefinery, essentially from biodiesel, because this can be converted on the other side to formate. In this way, we paired two reactions, but to give some product. And of course, this is increasing the total efficiency and productivity of the overall system. And also this system was scaled up to something like 0.2 square meter size. Next slide, the number 9. Here we see the electrode. Apparently seems non-homogeneous, but is a really homogeneous system. We arrived to this after, of course, several testing of different material that, again, I don't put for confidentiality the specific type, but you see that, of course, there are quite different performance, and we obtain at the end a relatively stable and a relatively good performance on the final electrode that we have developed. The next, the number 10. Here we see some of the results of the system. So you see the two paired reaction. You see that we are forming exactly the same product at the end of the two sides, but of course we are starting from different feed, CO2 from one side, the cathodic, and glycerol from the anodic side. And we see that also in this case, we have a really good performance and stable performance up to over 100 hours of time. And formally, the total Faraday efficiency summed is 160%, more than 160%, which is of course the sum of the two cathodic and anodic reactions. The next one, the number 11, I just mentioned that we have introduced the controlling unit by the impedance spectroscopy, which is very useful because this is something again unique in often in electrochemistry, but from industrial point of view is very important because allowed exactly to determine where are the performance, if there is need to change, if something happened, and also for security, because if something happened, can be immediately stopped and put in security all the system. The next one is the 12. We have worked also on carboxylated salt splitting. Again, this is a technology that I think is more common because often in electrochemistry you form the salt due to electrolyte, and then you need to convert to the acid, and this can be made by electrochemistry. We give you a system which is much more integrated and that can be very good integrated in the system. Here are bipolar membrane which are used. We have developed the system up to 3L5. You see some of the picture of the system is a very compact design and definitely much better than other possibilities that can exist in terms of this. For example, if you think the most common, which are using classical membrane, we are making this under ambient pressure, and we don't need to have compression. And also we have a much more compact system. Next slide, number 13, and now also was working. This was tested using real feed and, for example, containerized high content of potassium, and let me say that the performance are really good and quite encouraging for using this kind of technology. The next one, the number 14, and so last part is dedicated to developing of the electrochemical hydrogenation of oxalate. And again, here we were starting, because it was not essentially or very minimum data in literature on this, and so we started from screening of the catalyst, then optimization, and finally we are now at the test to feed the real feed and to test also stability up to TRL4. And here, of course, mainly activity was from academic side. Here is the reaction of oxalic acid. You see that you have a multi-steps reduction to go to glyoxalic acid, glycolic acid, and then if you continue to go to ethylene glycol. Initially, there was to arrive to ethylene glycol because, of course, it's quite interesting raw material. But at the end, if you analyze the cost, because of course you need to have more electrons, so it's more difficult to obtain. But also, if you compare in terms of advantage or added values of the product, possibility to make and consumption of electron, which is a cost. Then you see that the glycolic acid is probably the best combination and best target. And you see on the right some of the lab scale reactor that in this case was used. Next slide, number 16. What you see is that, for example, by simple cyclic voltammetry, that you have a drastic effect of the presence of oxalate, which means that you transport. In this case, after several trials and tests, we arrived at the best electrode is based on titanium in the form of a film of titanium nanotubes. You see here some of the elements of the structure of this thin film. You see that they are well aligned titanium oxide nanotubes that can be produced by anodic oxidation up to a really large and uniform cell. This is not an effective catalyst, but is a kind of titanium oxide debates which are on the top of this layer, but which has enhanced redox performance and also stabilization due to this interaction with this film of titanium nanotubes, which help also to maintain the electronic contact with the Nafion membrane. What is important is that this is something unique, because normally you don't consider that an oxide like titanium oxide is a good hydrogenation or electrocatalytic hydrogenation catalyst. Normally you consider to have metals, but of course the typical problem that you have with all metals is that oxalic acid is a strong complexing agent, and so is dissolving, and you don't obtain very good stability in most of the practical system. This is the reason why we arrived to this system as the best. Next slide, the number 17. Here are some elements of the synthesis route. The synthesis is very important. We have compared, for example, different preparation way. Just summarize here, for example, the possibility to obtain a kind of nanostructure by hydrothermal system or by anodic oxidation. And you see here some of the elements in the preparation. Next slide. What you see here in the next slide is that you have the anodization curve that you obtain during the preparation. So essentially, what is the process? The process that you, when you start anodization, you first form an oxide layer, and this is the reason why you decrease the conductivity. And then you start to have a reconstruction of these. and you can have different kind of reconstruction. You can form a kind of disordered layer like you see in the bottom electron microscope, or you form a kind of more ordered and in the form of titanium nanotubes array on the top. So this, of course, depends on the condition of preparation and how you can optimize the different elements. So you have a variety of possibility by changing and by controlling the preparation. And the next slide, the number 19. If you can try to analyze how the different performance are of the different systems, then you see that you can try to correlate the behavior to different systems. For example, if you just have a kind of disordered nanostructure, the titanium oxide, you try to form especially the glycerolic acid. On the contrary, if you have this kind of situation in which you have ordered titanium nanotubes plus these debris of titanium, then you form the glycolic acid, and depending also on the other type of situation, then you can control and optimize the performance. Here you see, for example, a kind of summary how the different kind of nanostructure, you see on the bottom some example, you can try to change and to optimize the formation of glycolic acid. And this is exactly in relation to the number of defect oxygen vacancy which are formed in the system. You see that you can obtain a kind of linear correlation between this amount, which can be determined by XPS, for example. You see an example on the inset and the yield of glycolic acid. So this is just to give you an example that there is also a good science behind the development of this system, and you can optimize and you can choose. For example, you see that depending on the type of nanostructure that you obtain, you can maximize the formation of glyoxylic acid or of glycolic acid. So we have, of course, studied also the nature of the electroactive species, and is what I anticipated before. What we have identified is that the best system are a kind of small amorphous titanium oxide nanoparticles, which are needed to interact and to be supported on the these titanium nanotubes. We have also tested what happens if we remove these nanoparticles, or if we deposit this nanoparticle on a different substrate, or even on a titanium layer. So it's a different performance. So it's this unique combination of this system, which is important, and this also is a kind of unique type of selective hydrogenation electrocatalyst. Which is, there are few results on this type in literature, and open also to a number of other applications, because this possibility to make electrosynthesis by hydrogenation is an area which is growing, and there are many other applications. So with this, thanks again for attention, and again, my excuse and apologize for all the problems that we had this morning.
Thank you, Professor Senti. And thanks for giving two presentations after each other. It's difficult, and we were happy to see your first presentation that you could not give today in the morning. So I don't want to waste more time. So the next presentation is from Arno Mol. He's an engineer at Avantium, a leading technology company from the Netherlands in renewable chemistry. He has been working for Avantium for 15 years, and the last 5 years in the field of electrochemistry with Volta. And now he's going to give you a presentation about the development of the demonstrator unit Professor Senti was talking about. Arno, the floor is yours.
Thank you very much for the introduction, Swan. Yes, so welcome to the next part of the eCCU3 workshop. So my name is Arnoud Mol, and I would like to share the development of the demonstrator unit, which was developed within the Ocean project. I'll start with a short introduction on Aventium and on the Ocean project. But after that, I'll dive a bit deeper into the Ocean demonstrator and talk a bit about the process and the economics. So starting with Aventium. So Aventium is a leading technology company from the Netherlands. The renewable chemistry department develops innovative plant-based chemicals and materials from non-food resources. So if we move to slide number 3, so Aventium is a pioneer in the emerging industry of renewable and sustainable chemistry. We're headquartered in Amsterdam, and we have approximately 250 people working with an extensive R&D laboratories and 3 pilot plants in the Netherlands. The electrochemical department of Aventium is called Volta, and I'll show you that in the next slide, which is number 4. So Aventium's Volta technology is a platform technology that uses electrochemistry to convert CO2 into high-value products and chemical building blocks such as glycolic acid and glycolic acid. These products are predominantly used in cosmetics and polyesters. The Ocean project consists of multiple electrochemical processes, so therefore it's, let's say, a perfect fit for the Volta technology. So if you then go to the next slide, so this is a very brief overview of the Ocean project. So the Ocean project targets to produce C1 and C2 intermediates, starting from industrial CO2 through multiple stages. This is done by using electrocatalysis. The C1 and C2 intermediates are converted into value products and monomers. And in the final stage, so we target to make polymers out of the C2 intermediates such as oxalic acid and glycolic acid. This of course involves all the a collaboration of all the 7 partners within the Ocean project. And for this presentation, I'll mainly focus on the second stage, which is the electrocatalysis under the industrial conditions. So this is shown on the next slide, number 6. So in this second stage is where the Ocean project addresses the critical elements in the development of new electrochemical processes. At the start of the project, we looked into the catalyst optimization and the upscaling of the electrodes and the technology. New electrical chemical methods were developed for the acidification of potassium formate. And so the phase we're now in is the industrial feasibility of the electrochemical process. This is done by engineering and manufacturing the pilot unit that you've seen before in the video. And this one is now being tested at RWE under industrial conditions. So this is where we are, let's say, currently within the project. So let's go a bit into the electrochemistry. So it's shown on slide 7. So electrochemistry provides, let's say, free solutions. It avoids CO2 emissions, but it also, let's say, unlocks a renewable carbon source from above the ground. And well, last but not least, it uses the cleanest reagents by using electrons. So a very simple overview of electrolysis, which is shown on slide 8, consists of if you look at a cell, you will have a cathodic and an anodic side with a membrane in the middle. So when we feed water to it and we apply electricity, it will start to produce hydrogen and oxygen. And well, the more electricity we apply, the higher the production rate is. So what we do is this is shown on slide 9. So when we feed CO2 into the system at the cathode side, it will start to produce products. So within the Ocean project, we target the production of potassium formate, which is a chemical building block. There are, let's say, 2 important factors here. So one is, so how do we introduce the CO2 into the system? So this is very, let's say, is key to, let's say, upscaling this technology to a higher level, but also, of course, how efficient our catalyst is. So this is basically how much electricity is being used for the reaction of CO2 to formate, and instead of the hydrogen production. So moving on to the next slide, on the left side, you can see there are different ways to feed CO2 into a electrochemical cell. And each has its own advantage and disadvantage. You can use a flat electrode or a 2D electrode or a porous 3D electrode, or you can use a gas diffusion electrode, which is in the top right corner of the left picture. A gas diffusion electrode have a unique technical advantage in mass transfer and diffusion limitations. In a global literature review, which is shown on the right side, the efficiency is compared between different scales and the type of electrodes. So at small scale, nearly all type of electrodes can achieve a high efficiency towards potassium formate. However, as the scale increases, most types of electrodes will decrease their efficiency. However, the GDE type of electrodes, they show a high efficiency at large scale as well. And therefore, within Ocean, we use these gas diffusion electrodes for our electrochemical cell. So moving on to slide 11, we can see the Ocean demonstrator, which we saw earlier in the movie. It's a TRL 6 unit, which is developed by Aventium and manufactured by HySitech. It has a 1 meter high electrochemical cell, which we can use to test the gas diffusion electrodes. The electrochemical cell itself is designed and manufactured by Aventium and HySitech. However, the gas diffusion layer, that part has been upscaled by Gasketel, and you can see an example of that in the bottom right corner. They can produce the gas diffusion layer, let's say, on a roll, and we can spray our catalyst on this layer. and then we can put it in our electrochemical cell. We target to convert half a kilo of CO2 per hour, and this is done at room temperature and at atmospheric pressure. So far we've only looked at the cathode side of the electrochemical cell. However, at the anode side, so the positive side, we can split water into oxygen. However, to optimize the process, we have changed the anodic reaction. So if you move to slide 12, the paired electrolysis, so that's the co-production of a valuable chemical at both sides of the electrochemical cell. So this allows two reactions to be performed at once. So it has the advantage that you use, let's say, the same electron twice. It lowers the water consumption, and you upgrade a bio-based feedstock. However, there are also factors which make it more challenging. You have to match the current density. So how much current do you apply per area of the electrode? You have to match it from for the anode and the cathode side. We also have to look into the pH compatibility of the membrane. And of course, if you upscale two reactions at the same time, it takes more time and effort. So if you move to slide 13, so for the Ocean project, we have selected the glycerol oxidation to be paired with the CO2 reduction. Glycerol is a byproduct of biodiesel production and can be split into 3 formate ions. By producing formate on both sides of the cell, so the cathode and the anode side, we increase the production rate of the cell and therefore reduce the amount of energy required to meet a certain production. And another advantage is that we can also combine the downstream separation, which will save a lot of cost. So within the Ocean project, we went from lab scale to TRL6 within 4 years with this anodic reaction. It is so another point is that it is a high pH reaction, which makes it less ideal compared to a low pH reaction because we have to use a bipolar membrane instead of a cation exchange membrane, and a bipolar membrane in general has a higher potential and will increase the operational cost in the end. So moving on to slide 14. So paired electrolysis has its advantages, but yeah, how is the efficiency in the process? So figure on the left shows the results that we have obtained in the Ocean process. The paired electrolysis, so if you look on the left side, so that's on the lab scale, so that's done at 10 and 100 square centimeter. And we've used the current density of 100 milliamps per square centimeter. And as you can see, for both reactions, the efficiency is about 80% for each side, which is really good. So for the coming period, we are planning to with the container at RWE, we're planning to perform this paired electrolysis at larger scale as well, so at 0.2 and at 1.4 kilograms per hour. So this will happen in the coming months, where we will transfer the operation from Aventium to RWE. And we will look at parameters such as the stability of the electrodes and the effect of industrial CO2 compared to commercial CO2. And finally, the potassium formate that we produce will be shipped to other partners within the project, where we will use that to produce potassium oxalate and finally oxalic acid. Moving on to slide 15. So another part of the ocean project, well, involves looking into the future. So going from pre-pilot to a actual plant. So which factors are important for scaling up and which product should we select? So starting from CO2, we can make a lot of different products. So for the ocean project, we have selected formate because it's a building block for formic acid and oxalic acid. So we also need to look at, let's say, the process, the hardware, so how do we scale up, and the market. So moving on to slide 16. So here we can, so on the right side, you can see a sensitivity analysis for a larger plant which forms or produces formic acid. So we've done multiple sensitivity analysis on different products, but for this example, I'm using formic acid. And as you can see that there are some technical risks which can have, let's say, a high impact on the economics of a bigger plant. So which are, of course, the cost for the electrochemical cell, the cell voltage, but also the current density. But it's not all, let's say, the major parts that have a the largest impact are not per se the technical risk, but the economic inputs and constraints of the model also have a large impact. So these are the formic acid market price, but also the feedstock, so the CO2 and the electricity price. I mean, they have a large influence on the economics of such a large plant. So therefore, it's not important to only focus on the technical aspects of the process, but we have to work together with the CO2 and energy suppliers and the politicians to make the next step. I think in view of time, I'll just move on to slide number 18. So I would like to end this with a example of of how a big plant could look like. So as you can see here, the electrodes are 3 meters wide, and they're about 50 to 100 cells stacked together. So let's hope that we get there together. And with that, I would like to thank you for your attention.
Thank you, Arno. I'm afraid that we do not have the time for the Q&A right now because we want to give everybody the chance to have a break, to come back with a fresh mind to the last session, which is about eco-to-fuel. So, but nevertheless, these questions which we have received for the ocean project, they are going to be answered privately. So if you have left us your email address, we are going to contact you then separately. So thanks again, everybody, for joining this session on the ocean project. And we will be back at 3:30 with the session on the eco-to-fuel project, where we are going to have some presentation on low temperature CO2 reduction to carbonaceous fuels design to realization, and the economic and environmental aspect of the electrochemical CO2 conversion to carbon neutral fuels and chemicals. Thanks a lot, and see you in a bit.